This week, the little darlings are going to take me to a sewage plant. Really. Then there's a piece on what video is. But first, here's how a telephone works. You know, my cousin's a telephone.
Do you work for the phone company? Please switch to another channel then. A few years ago, I would have been afraid to stand here and discuss how a phone line works, but times have changed. In the old days, the phone company was very picky about what you connected to the line. Now, anything goes. The basic phone was invented by Alexander Graham Bell, and the classic telephone is much the same as his invention. Bell, though, didn't invent the bell. Thomas Watson, his assistant, invented the bell. Another Tom, Edison, invented the microphone that was used in it. And so the phone remained for about 70 years. The telephone company had a good reason to keep it that way, too. It worked, was rugged, and was compatible with millions of other phones in North America. The difference between these two phones is more than meets the eye or slips off the shoulder. Why can't they do something about that? To understand what's happening to telephones, you have to know about the local loop. The phone companies evolved and changed over the years, moving to electronic switching and fiber optics and a lot of other innovations, but not yet on the local loop. The local loop is the direct wired connection from your phone to the nearest exchange. Now, you might see up to 4 wires coming out of your phone, but most local loops use only 2 wires. That saves a lot of wire. The length of your local loop might vary from a few hundred feet to several miles, depending on your location. The same 2 wires have to carry two-way conversations, signal that there's a call for you, and most important, let the phone company know when you lift the handset. It's a little-known fact that I own a phone company. I build it myself. Notice that the only connection to the phone is by these 2 wires. When the phone's hung up, it isn't connected to the line, and no current flows between it and the phone company. There's no dial tone on the line either. The phone system's ignoring the phone. When you lift the handset, current flows in the loop, and the system finds an active circuit in the exchange and connects you and gives you a dial tone to let you know you can start dialing. Now, if the phone's disconnected when it's hung up, how can the bell ring? Easy. The bell is always connected to the line, but it won't pass the direct current, DC, that's present on the line. It'll only pass alternating current, AC. The alternating current can come from the phone company or from electrical storms. If you live in the country with a long local loop, you know what I mean about electrical storms. Incidentally, there's a reason that the signal rings and then pauses and then rings and then pauses. The pause is there so that the equipment at the phone company can tell if you've picked up your phone yet. Now, the final thing you have to be able to do across the same 2 wires is reach out and touch someone, as we say in the phone bids. The way to do that for years was the rotary dial. With the handset in your hand, the current flowing, the dial interrupts the current at a rate of 10 pulses per second. The number of pulses is the same as the digit you're dialing. 1, 2, 3, 4, so on. The original switch that used to select lines worked something like this one. This is actually part of an old jukebox. The phone company's switch had more ratchets and wipers. It was invented by an undertaker named Almond B. Stroger. His competitor's wife, you see, was the town switchboard operator, and if she'd sent Stroger more calls, we might never have had dial telephones. Now, astute observers are saying to themselves, but by gum, that dial thingy is putting alternating current on the line. How come the bell isn't dinging when I dial? You know, they thought of that. During dialing, the switch, right here, shorts out the bell. It's known officially as the anti-tinkle circuit. The anti-tinkle switch only shorts the bell in the unit that's dialing. In the country with long local loops, due to a property of long lengths of wire called inductance, dialing tinkle is heard on extension phones. Of course, touch-tone dialing is rapidly replacing pulse dialing, but there are still some exchanges that don't understand the tones. By the way, if you want to impress your friends, the proper name for touch-tone is dual-tone multi-frequency, DTMF. Now, this configuration of phone is rugged, functional, and downright clever. 2 astounding features of its design have to be stated. It's not connected in any way to local household power. You can still phone the electric company to complain of a power failure. When it's on hook, it draws no power from the phone company either. Every single component in it is passive. It performs all of its tricks by allowing current to pass when you pick it up, pulsing that current with the dial, then wiggling that same current with speech. It's simple, efficient, elegant. Couldn't last, could it? It'd be nice to redesign the local loop to take advantage of modern electronics, but that would mean discarding a few million phones. So for now, electronic phones have to do their best to simulate Old Faithful. When the tone's set to pulse, it will simulate the clockwork mechanism of the old-fashioned dial. Now, no matter how fast you push the buttons, it'll put out that stream of pulses at 10 per second. And because you can finish pushing long before it can finish dialing, there has to be enough memory on board to store one whole number, area code and all. So don't be too impressed with last number redial. The memory had to be there anyway. You know, a funny kind of reversal of the way things usually go. Something's lost by using space-age electronics on the local loop. Electronic phones do draw current from the phone company when they're on hook. Enough to keep the electronics awake enough to recognize a ringing signal, and to power whatever it is that makes that stupid sound that replaces the bell. The standby current on these things is low, but it varies from unit to unit. If enough of them are connected to the line, enough current can be drawn that the phone company might not be able to distinguish whether you're off or on hook. So now that it's up to you to decide what to connect to your own line, there has to be some sort of method of imposing order on the potential chaos. If you go wild with answering machines, auto dialers, auto answer modems, and extension phones, you can potentially mess up your local loop. So for that reason, the non-phone company equipment is appearing with a load number. I have an answering machine that's an 11. The grand piano here is a 12. The cordless is a 15, and so on. It's up to you to add up the numbers and make sure they don't exceed 100. Otherwise, you don't say. You don't say. You don't say.
Who was it?
You didn't say.
Darn it.
This is the city. 3 million people. Working, eating, sleeping, washing, flushing toilets. One of the nice things about being part of a city is not having to worry about your own waste. One whoosh and it's gone. We decided to follow it. Feel free to say yuck anytime you like, but remember, it's your sewage. Incoming sewage to this plant is a collection of stuff with an interesting recipe. Take the output from toilets, sinks, showers, add anything that might be washed down the city's storm drains, and sprinkle with industrial waste. One fellow at the plant called it a witch's brew. The exact components change with the season and time of day. This is the first step in treating the mystery water, the grit tanks. The sewage is actually moving lengthways in these pools away from us. The sideways motion you see is caused by aerators that keep the mixture mixed. At the far end of the pools, it swoops below into a screen that will catch large objects. The screens are continuous belts that rotate periodically. Up top, solids are scraped into bins and trucked away. The screens catch cloth, cardboard, plastics, and rubber. After being relieved of its large hunks, it's onto these pools. Several things happen here. Grease floats to the top and sludge sinks to the bottom, and concentrated laundry bleach is added to knock off some of the bacteria. The bridge across this pool is actually moving. At the moment, it's returning to the far end to begin a new sweep. It will slowly shove the grease on top towards a conveyor at this end. From the settling pools, there are two different processes. one for liquids, another for sludge and grease. Sludge is pumped from the bottom of the pool. The sludge and grease are reunited in a digester. We were having a good time in the underground tunnels to the digesters until we heard stories of monster spiders. Here's a shot from the roof. The round buildings are the digesters. There are 12 of them. Each one holds 1 million gallons of gunk for up to a month. Inside, sludge and grease digest in a heated environment much like your tummy. We were lucky enough to see a digester being emptied and cleaned. The video doesn't do this justice. You had to be there. Sludge is pumped out and then undigestible stuff is picked out by hand. The output of a working digester is much like the output of a human stomach. The gas, methane, is partially recycled to heat the digesters. There's no one procedure to treating sewage. At various points, the mixtures may be sent back to the beginning for reprocessing or elsewhere for further processing. These are big pressure cookers that will break down the sludge molecule so that it will give up its water easily. This is the dewatering process. After digested sludge has its water removed, it goes on to an incinerator. The incinerators are multi-story affairs that receive the dewatered sludge at the top. How hot are the incinerators? Hot enough to burn damp sludge. That's how hot. It turns into ash. Smoke from the incinerator has a fine mist of water sprayed into it to capture any solids. All liquid from the plant is sent to a huge array of pools. Any sludge that forms on the bottom is sent back to the beginning for reprocessing. Aerobic bacteria in the pools, sunlight, and fresh air help to purify the water. And it's given a final shot of bleach before it's returned to the lake. This plant operates 24 hours a day, all year, providing a vital service to the city. Even as we sit back and burp after our holiday dinners, someone's taking care of the stuff we send down the drain. Not only is the word video battered around in all sorts of ways these days, but Mr. Webster here defines it as the opposite of audio. Helpful. Thorndike and Barnhart over here define it as pertaining to television, but they insist it's an adjective. So, what is video? That was video. Thorndike and Barnhart also point out that the word video is Latin for I see. I see. Video. See? Video is a varying voltage like audio, but the similarity ends there. Now, first of all, there's a 99% chance that the video you're watching right now is coming to you as a radio signal. If you're watching off air, our video signal is modulating a high-frequency radio transmitter, and our audio is modulating a similar transmitter operating on a different frequency. Your TV set is tuning in both of those transmissions simultaneously. If you're watching this on a VCR, nutty, the video is probably undergoing the same process. There's a small transmitter in the machine. Its output is labeled RF out. The RF stands for radio frequency. If you're using the video and audio connectors, you actually have video in your house. Video is an analog serial signal. Imagine the signals that this computer is sending to this dot matrix printer. As the printhead scans across the page, the computer has loaded the printer with a bunch of on and off pulses that control whether each one of the little pins in the head should poke the ribbon or not poke the ribbon. At the end of each line, the computer's added a signal that returns the printhead to the left to begin a new line. In other words, the picture is being sent along the wire to the printer bit by bit, sequentially. The printer actually has 9 little wires in its printhead that can poke or not poke the ribbon. If this were exactly like video, 2 things would be different. The printhead would only have 1 poker in it, but the poker would be able to print various shades of gray in any one spot. There is one thing that's like video though. If the printer were allowed to return the printhead to the left anytime it felt like it, this wouldn't be a picture anymore, just a mess of dots. A video signal is also sent sequentially, with things called synchronizing pulses inserted to keep the monitor or TV set in step. Now, video isn't a series of dots, no matter what you might hear. Video is a continuous analog signal. It changes to represent the instantaneous brightness of the picture it represents. The picture that video makes is made up of lines, however, 525 of them in North America. Here's how video prints a picture. This electron beam starts sweeping from the left to right at the top of the picture, and the video varies the brightness of the beam from dark to light as necessary. At the right side of the picture, the video signal suddenly dives to a voltage level much blacker than black, signaling to the display to return the scanning beam quickly to the left. This process continues until 262.5 lines have been displayed. Then the video takes another plunge, but that time it was of a lot longer duration. That signals the display to return the beam to the top of the picture. The beam goes up there quickly, offset by 1/2 line. This places the next 262.5 scan lines between the first group. When 262.5 lines have been displayed, the beam's now at the lower right corner of the picture. Why? Well, this method of interlacing the scanning reduces the flicker without increasing the amount of picture details that have to be sent. The apparent flicker rate is 60 pictures per second, while in actual fact only 30 pictures per second are displayed. The 2 interwoven parts of the picture are called fields, and the pair of fields is called a frame. Here's a still frame of video. It's the 2 interlaced fields being reproduced over and over. During the time the 2 fields were scanned by the camera, some motion occurred on the dolphin. Now, we can get a better freeze by using only 1 field and bobbling it up and down by 1 line to fake the interlace. There it is. Watch the openings and closings of shows that use freezes of the actors, and you'll spot a lot of freeze frames with motion jitter here and there. If there is no motion, though, a freeze frame is better because it has more details than a freeze field. And the amount of details you can see in video depends on various things. Things running horizontally rely on the vertical resolution, and things running vertically depend on the horizontal resolution. This is video showing its sync pulses. The vertical sync intervals here and the horizontal sync intervals here. The vertical sync interval actually lasts for about 21 scanning lines in each field. That only leaves about 480 lines that can have pictures in them. Now, any parts of the picture that have details running this way will be at the mercy of the scanning line pattern. A picture of 500 horizontal stripes would get lost between the lines. A picture of vertical stripes depends on how fast the video can change from dark to light. That depends on the good old frequency response of every step in the process. Our pictures leave here with an upper frequency limit of 4.2 million cycles per second. Now, what you see at home depends on your receiver. The frequency response of a video device is often stated in lines, and that has absolutely nothing to do with the number of scanning lines. It's always 525. The lines of resolution refer to how many fine black and white lines this way could be seen if the screen was covered with them. In printing, they use lines per inch for their specification, but see, we don't know how many inches your screen is, so we use lines per screen. Once you try to display too many vertical lines, they just blend into gray. This is our resolution chart. It's used to check the camera. The wedge-shaped areas read resolution directly. Wherever they blend to gray is the limit of the system. We can see about 400 lines of resolution. If you're lucky at home, you'll see about 350 off air. If you recorded this, what are you doing recording this? You'll see even less. This is a resolution test pattern. The inset on your screen now is an oscilloscope showing the video signal. It's a picture of bars getting thinner and thinner going towards the right. And the thinner and thinner bars represent higher and higher frequencies. More details. Notice the dip down at the right of the oscilloscope. That's a horizontal sync pulse. Now, this is the same pattern being played back through a home VCR. The finer details are there, but they just don't have the same amplitude. They appear on the monitor to have less contrast. Here's, color. Where'd the color come from? Well, at the camera and the TV, there are three of everything. A red one, a green one, and a blue one. These three colors mixed together produce everything you see on a color TV. And one way to send you this video would be on 3 separate video cables, or by 3 separate transmitters. Some computers feed their monitors that way with the RGB cable. For ease of broadcast and recording, the video we use in television is encoded. The red, green, and blue signals from the camera are mixed in the same proportion that would make white in the real world. The encoder makes 2 signals. One looks exactly like the picture with no color. Superimposed on that video is a signal called the subcarrier. Now the video still controls the brightness of each point in the picture, and the subcarrier controls the hue and saturation. Look at the color bars again. I'm going to turn the color subcarrier off. It's a picture of bars from white to black and back up again. Here's the subcarrier on again. Notice on the scope, there's no subcarrier on the white bar, and the gray and black bars don't have any either. A black and white monitor will ignore the subcarrier and produce a compatible black and white picture. The amount of subcarrier indicates how saturated a color is. Blown up big, the subcarrier looks like this. It's its time relationship to a reference that determines the hue of the display picture. Now, we could have an incredibly accurate time reference built into your TV set. But instead, we have that time reference at the station. And right after the horizontal sync pulse, we send a little piece of it that the set can latch onto. It's called the color burst. And that's video, as we know it, and your set gets it, and your VCR records it. It's a serial, analog signal embedded with sync pulses mixed with a subcarrier that makes color pictures when connected to a suitable display device. Take that, Mr. Webster. In our next program, we're going to look at how batteries work, how electronic fuel injection works, and we're going to take a little bus trip to a water treatment plant. I wonder what he uses this stuff for anyway.